Okay, this is section 8.4. We're dealing with vectors, vector operations, and dot product. This is part 1. There's 2 parts to this section. We're only going to get to vector operations in this first part. We'll deal with dot product in the next section, in the next part of this video. Alright, so the goals of this section are to become familiar with the algebraic interpretation of vectors, to know what the magnitude of a vector is, to know what the direction, how to figure out the direction of a vector, to figure out its horizontal and the horizontal and vertical components of a vector, to be able to add, subtract, and multiply vectors. Well, add, subtract, and do some other operations with vectors. You're gonna wanna know what is a unit vector and what is the dot product. Okay, the dot product will be covered in the next video. Some preliminaries, well, pretty much any trigonometry that we've done so far is fair game. Distance formula, Pythagorean theorem. Okay, so let's start thinking about vectors then. What is a vector? So a vector, you can think about it as a directed line segment. So a line segment is just a line between 2 points. That's what a line segment is. The fact that it's directed means that it has a direction. Okay, so you have 2 points. You have the point O and you have the point P. And there's a line between these 2 points. And there's a direction from O to P. I'm going to call O the initial point. I'm going to call P the terminal point. And right now the direction starts at O and it goes to P. That is my vector. I can denote the vector by using this type of notation. This guy says U, and then there's this little line up here indicating that it's a vector. Sometimes you just see U or V. They're usually bold letters. Or you can also think of vectors in this form. It's O to P, and then there's this upper line here which indicates which direction the vector is going. It's going from O to the point P, which is very different than going from the point P to the point O. They would be going in opposite directions. So vectors have a direction. They point in a certain direction. We're going to be interested in finding the direction in which they point. So just be aware of the notation. Sometimes there's this notation with the little arrow. Sometimes there isn't. We might use that. They all stand for vectors. All right, so let's add some vectors graphically. So I can add 2 vectors. I have the vector u and the vector v. I can add them by setting the terminal point of one together with the initial point of the other. So for instance, right now the terminal point of u joins the initial point of v, and that creates the sum u plus v. This new vector over here in red called u plus v, it's a brand new vector. It has its own direction. It's different than the direction of u and the direction of v. There's this other more common way of adding vectors. It deals with what's called the parallelogram rule. And it's that you put the initial points together. So I have put the initial point of u and the initial point of v together. And then what happens here is you sketch a little parallelogram. So I am going to, here at the terminal point of u, I'm going to sketch the vector v, starting from the terminal point of u. And then from the terminal point of v, I sketch the vector u. And that creates a little parallelogram. And the sum of my vectors is the main diagonal of that parallelogram. This new vector u plus v is called the resultant vector. So resultant is just the sum of 2 vectors, or the difference of 2 vectors. Alright, so now let's think about the algebraic interpretation of vectors. Think about, in this previous discussion up here, if you notice, our vectors are just floating in space or in the plane. There's no point of reference for anything. I'm just drawing vectors. Now here for the algebraic interpretation of vectors, I am going to draw vectors in the Cartesian plane. That's the algebraic interpretation. All of a sudden you have a point of reference, the origin. Alright, so here I have a vector, I'm calling it u. Its initial point is at the origin. Its terminal point, well, it's over here, it's this point a comma b. Yeah? And there's an angle, theta, that is created between the positive x-axis and my vector. That angle theta is going to be the direction of my vector. Right now, the angle u, the vector u is called, it's in what's called position vector. Position vector just means that the initial point is at the origin and its terminal point is wherever in the Cartesian plane. Notice that in order to denote vectors, we use this little, I don't know what to call them, little brackets, little corner brackets, yeah? So these little sharp brackets are to indicate vectors, whereas parentheses were to indicate points. So be aware, this is not a point right here. This is not a point. This is a vector. And you can tell vectors by this special little brackets. This guy's a point. This has parentheses, so that's a point. So in this picture, A is called the horizontal component of my vector. B is called the vertical component of my vector. Every vector has what's called a magnitude. And the magnitude is just the length of the vector. And it's denoted by absolute value of the vector. So we're going to use absolute value signs to indicate magnitude. So if you see absolute value signs, that just means magnitude of the vector. And it's the length of the vector. Well, how do you find the length of a vector? Well, in this case, we could just think about the distance formula. I mean, we have this point, the terminal point, a comma b. We have the initial point, 0, 0. And we'll just find the distance between these 2 points. What's the distance between these 2 points? Well, it's this x-coordinate minus that x-coordinate squared plus this y-coordinate minus that y-coordinate squared. We'll take the square root of that. So we end up with this expression. This is the magnitude. This is how I find the magnitude for a vector in standard in position form. So be aware of this. This is our little formula for the magnitude of a vector. This tells us how long the vector is. A vector is made up of 2 things, a direction and a magnitude. Well, the direction angle is this angle theta. And if you look at this picture here, well, what we're going to say is that tangent of this angle theta should be opposite over adjacent. So tangent of theta is opposite over adjacent. And that's going to help us find that right there. So tangent of theta equals opposite over adjacent. Just of course if a is not 0. And so then theta is going to be the tangent inverse of b over a. And remember that the range of tangent inverse is negative pi over 2 to pi over 2. So you might want to adjust the angle to some coterminal angle later down the line if you're trying to find the direction of a vector. Alright, so let's recap this real quick. We have u in position. This is a position vector. A is its horizontal component. B is its vertical component. The magnitude of this vector, remember the magnitude is this absolute value. The absolute value of u means the magnitude of the vector u is the square root of the horizontal component squared plus the vertical component squared. To find the direction angle, you gotta think tangent of theta equals opposite over adjacent, and then you have to take tangent inverse to find the direction angle. And you might have to adjust the direction angle to some coterminal angle. Alright, horizontal and vertical components of a vector. So we said that A was its horizontal component, B b is the vertical component. Right now I have some vector u right here. And now notice that cosine of theta is adjacent over hypotenuse. The hypotenuse in our case would be the magnitude of u. So a over the magnitude of u, the length of this diagonal. Well, the length of that diagonal, that's the length of my vector. That's called the magnitude. So then cosine of theta is adjacent over hypotenuse. And my adjacent is a, my hypotenuse is the magnitude of my vector. Sine of theta is opposite over hypotenuse. So b over hypotenuse. And if you notice here, I can solve for a and I can solve for b by multiplying both sides by the magnitude of u. And so then I have this expression right here for my horizontal component. I have this other expression for my vertical component. So this vector u has horizontal component a. The horizontal component a can also be thought of about, it's equivalent to the magnitude of the vector times cosine of theta. Theta is the angle between the x-axis, and it's the positive angle between the x-axis and my vector. The vertical component can be thought about it as the magnitude times sine of theta. So this is important right here. This can sort of help us figure out the vertical and horizontal components of our vectors. All right, position vector. I just want to let you know. So we're going to be in these examples. We're going to see we're going to be asked to find position vectors or component form of vectors. What that just means is that you want to put the vector in the form a comma b with these pointy brackets. So position vector, component form of vector just means put the vector in this form. All right, let's get into some exercises then. So at this point, pause the video, take a couple of minutes, see if you can solve it on your own. What we have to do is we are given this vector u in position form. We're supposed to find the magnitude and the direction angle of u. So pause the video, see if you can tackle it on your own. And then check the answers. Okay, so let's try to solve this. Let's first find the magnitude. So the magnitude of u is going to be the square root of the horizontal component squared plus the vertical component squared. Okay, so that gives me 4 plus 49, so the square root of 53. I don't think we can simplify that any further because I think 53 is a prime number. Okay, so that is what we get. Okay, next. The next thing we gotta do is find the direction angle of u. So we gotta find the direction angle of u. So what I'm gonna say is that theta is supposed to be equal to tangent inverse, and then it would have been, well, in our case it's going to be 7 over 2. And here what I should have done is I should have just maybe drawn a little picture of what's going on here so that you sort of get an idea. So I have 1, 2, 3, 4, 5, 6, 7. And that's that point. And my vector sort of looks like that. Yeah, this is the vector u. That's the vector u. And I have some angle theta right there. That's what I'm after, yeah? So that's what we're trying to find. So theta is equal to, so according to relative to this angle theta right here, tangent is supposed to be opposite over adjacent. So 7 over 2, that's why I'm taking tangent inverse of 7 over 2. And if I punch that into my calculator, and let's just agree for the rest of this section to have the calculator in degree mode. and let's round to the nearest tenth. Okay, so let me punch this into my calculator, making sure that it's in degree mode. Alright, so I get 74.1. So that's the angle, that's the direction angle of my vector. Alright, I hope that we agree on those answers. Let's move on to the next example. Alright, in the next example, what we are told is that the magnitude of my vector W is 25 and the direction angle is 41.7 degrees. I want to write the component form of W. What that means is I want to write W in the form A comma B. Yeah, that's what that means. Alright, so let's see, what should we do? Well, what you should do is you should pause this video and try to do it on your own. Just look back at the notes, think about what tools have we discussed that can help us with this. And well, what you should know, what we said is the following, that so we have W in what's called component form, and we said that the horizontal component can be expressed as the absolute value, or rather, the magnitude of W cosine of the angle, the direction angle, 41.7, comma, the magnitude of W sine of 41.7. And they told us that the magnitude was supposed to be 25. So 25 cosine 41.7, comma, 25 sine 41.7. And this is supposed to be, alright, I need my calculator for this. I need my calculator. Let's round to the nearest tenth and let's make sure our calculator is in degree mode. And if that's the case, then I get 18.7. That's my horizontal component, and my vertical component is 16.6. All right. So that's that for that example. We've written it in component form. Let's think about the next example. All right, in the next example, they told us that there's this vector u. They gave it to us so the horizontal component is supposed to be 4 cosine of 30 degrees, and the vertical component is supposed to be 4 sine of 30 degrees. We're supposed to find the position vector. So this is a straightforward little exercise here. What we just gotta do is use our calculator here. Well, actually, we don't even need to use our calculator because we know what cosine of 30 degrees is. It's in the unit circle. This is 4. Cosine of 30 degrees is the square root of 3 over 2. And for sine of 30 degrees, sine of 30 degrees is supposed to be 1/2. It is 1/2. It's not supposed to be. It's 1/2. Alright, well then, that becomes 4 times square root of 3 over 2. That's just 2 square root of 3, comma, 2. That is my position vector. Oops. All right. Next example. So two forces of 16 and 18 newtons. I'm not gonna get into what newtons are here, but maybe down the line in a second. So right now we just gotta think about them as vectors. So this is the magnitude of a vector, this is the magnitude of another vector. That's what that means. So I have two vectors, one with magnitude 16, the other one with magnitude 18. So these two vectors act on a plane. If the angle between the forces is 75 degrees, find the magnitude of the resultant force. This is an important example because other examples down the line cannot build on this one. So think about this example. Again, if I was you, I would pause the video. I would give me the opportunity to challenge myself to do this on my own. Take about 10 minutes. And then let's see if we can solve this together. Alright. There's a hint for this exercise. And it says that on a parallelogram, so this is a parallelogram right here. On a parallelogram, opposite angles are equal. So this angle over here and that angle should be equal. This angle and that angle should be equal. And that the sum of the interior angles of a parallelogram is 360 degrees, or 2 pi. Okay. Well, how are we going to use those hints to solve this? Well, let's see. Let's kind of try to set up the exercise here. Let's set up the exercise. And let me give myself room here, because I think this exercise requires a little bit of room. Okay, so let me begin by drawing a parallelogram. Well, first of all, I gotta think about my two vectors. Remember, there's these two vectors with magnitude 16 and 18. So the way I think maybe about it is like this. I'm gonna say that this guy right here, I'm gonna say, well, it's gonna be 16, its magnitude. I have another vector over here with magnitude 18, and it shouldn't be that much longer, something like that. This guy's 18, yeah. And okay, so the angle between them is supposed to be 75 degrees. And now, so yeah, so what's going on here is these two forces. So this force of 16 newtons, this force of 18 newtons is acting on like this point right here. And they're asking us to find the magnitude of the resultant force. Remember, the resultant force is the sum of these two vectors. So let me think about the sum. The sum is supposed to be, well, let me first draw a parallelogram here. That's an ugly parallelogram, but you get the idea. This is supposed to be 18 as well. This is supposed to be 16. Now, I am interested in finding, that is the resultant. I'm gonna call it R. So R is my resultant. It's the sum. Okay. Diagonal. And right now what we want is, we want to find, our goal is to find the magnitude of R. Well, that's the same thing as finding the absolute value of R, the magnitude of R. That's what we want to do. All right. Let's think about this hint that was given to us. So if this angle is 75 right here, that means that this angle up here should also be 75. Now think about what should be the measures of this angle and that angle. And remember that the sums of all four angles should add up to 360. So what is the measure of this angle and that angle? Well, 75 plus 75, that's 150. Now 360 minus 150 is what? 210? Okay, so 210. And so then I have 210 degrees, but then it has to be divided by 2 because I have these two angles are supposed to be equal. So 210 divided by 2, that's 105. So this should be 105 degrees. I hope that you agree with that, because then look, 75, this other angle is also 75, this angle is 105, and this angle is 105, and if you add all of that, that's 360 degrees. Okay. Now, okay, so great. Remember, right now, what's our goal? Our goal is to find the magnitude of the resultant. So I want to find the length of this diagonal. What can I do here to find the length? What tools do you know? What tools have we discussed in the previous sections? Law of cosines is going to be the ticket here. And what the law of cosine says is the following, that r squared. So look at this triangle right here. Yeah, I know this length, I know that length, I know the angle between them. So I should be able to find the angle opposite using the law of cosines. So r squared is equal to 18 squared plus 16 squared minus 2 times 18 times 16. That's an ugly 6. Cosine of 105 degrees. Alright, some arithmetic is going to happen here. This is 580 minus 576 cosine 105. I just use my calculator to figure these things out. Alright, and so then r squared. Now let me punch this into my calculator. My calculator is in degree mode. And I'm not going to round quite yet because I still need to take a square root. So I'm going to, let's see, I get 430.92 9202. Okay, well then r is the square root of that. 430.9202, and I get about 20.8. I guess we're dealing with forces, so this is newtons. And that is the magnitude of my resultant. So the law of cosines, good. If you thought that you could get away with it, well, you can't. It's going to haunt you for the rest of this section, at least, or this chapter. Okay, good. I hope that we agree on this answer. All right, the last thing in this for this part of this video, let's talk about operations with vectors. So let's begin. So I have A, B, C, D, and K. They are just real numbers. They could be decimals, they could be negative, they could be 0. They're real numbers. So how do you add vectors in component form? Well, so I have this vector right here plus another vector. Here I could have plus or minus. And well, you just see the horizontal component of the resultant is just the sums of the horizontals, or the horizontal components. The vertical component of the resultant is just the sum or difference of the vertical components. This is vector addition, subtraction. So you can add two vectors, subtract two vectors, and the result is a vector. There's another operation that we can do with vectors. You can multiply a real number times a vector. This is called scalar multiplication. Well, you multiply the real number times the horizontal component, and you multiply the real number times the vertical component. That's what scalar multiplication does. Scalar multiplication, what it does is it shrinks or lengthens the vector, or it changes the direction. If k, this value k is called a scalar. If the scalar is negative, then you change the direction of the vector. If the scalar is less than 1 and positive, it shrinks the direction. It shrinks the vector. If the scalar is positive and larger than 1, it stretches the vector. Okay. If u is equal to this component vector, then negative u just means negative 1 times u, and it's just negative a comma negative b. All right, let's see. Let's think about how this operations with vectors. So right now we have addition, subtraction, and scalar multiplication. So if I give you these two vectors, negative 2, 4, and 3, 5, I want you to find the following. U plus v, u minus v, 6 times u, and 4u minus 5v. I don't know, take about 5 minutes, pause the video, take about 5 minutes and see if you can answer these questions. Alright, so for u plus v, well, it's just going to come down to adding the horizontal components of my vectors. So negative 2 plus 3, just be careful with your signs. And the vertical component of the resultant is going to be 4 plus 5. Alright, so I guess that just comes down to 1, 9. If you were to graph the vector u in the Cartesian plane and the vector v in the Cartesian plane, and you joined their initial points, you put the initial points of both of them at the origin, then this resultant vector 1, 9 would be the diagonal between the two vectors. Alright, let's compute u minus v. So u minus v, so right now what I'm doing is just the horizontal component minus the horizontal component. So negative 2 minus 3, vertical component 4 minus 5. Alright, that's all there is to that. 6u, that just means 6 times my vector u, negative 2, 4. So that's going to become negative 12, 24. It just got stretched. My vector just got lengthened. Got stretched out. Alright, let's see. 4u, so that means 4, negative 2, 4, minus 5 times my vector v, 3, 5. Well, that's going to become negative 8, 16. Minus, you can then, so then we can say this, 15, 25. Alright, so then that's going to become negative 8 minus 15 and 16 minus 25. Negative 23 and 16 minus 25. Okay, so I hope that you agree with these answers and are comfortable with how to compute these types of things. Alright, next thing in this section, unit vectors. What's a unit vector? Remember, the unit circle meant a circle of radius 1. Well, a unit vector means a vector of magnitude 1. So the length of the vector is 1. There are two special unit vectors in the Cartesian plane. There's a vector called I, which is just 1, 0. It points in the positive x-axis. It's this guy in red down here. And then there's this other special unit vector called j, 0, 1. That guy points in the y direction. It goes all the way to 0, 1. So j is my vector that points in the y direction, I is my vector that points in the x direction, and they're both of magnitude 1. The unit vectors I and j are kind of like the building blocks for any other vector in the Cartesian plane. So if I give you a vector in the Cartesian plane in position form a comma b, then you can say, well, it's a times this vector 1, 0 plus b times the vector 0, 1, which just means that it's a times I plus b times j. Yeah, so for example, if I give you this vector -3, 7, well, that's just -3 times the vector I plus 7 times the vector j. So these two vectors right here, they are important for us. Keep them in mind. They're kind of like the building blocks for all of the other vectors in the Cartesian plane. All right, so I'm going to stop right here because otherwise this video will get too long. The next part of this video